This is sections 8.8 and 8.9 of Honors Algebra 2, Linear Interpolation. Oh, that sounds like fun. We'll get to linear interpolation in a few minutes. First, something different. The rational root theorem that we had in the last video and that we used in class the other day is incredibly useful in finding rational roots. In fact, it gives us a finite number of possible rational roots. And if we're going to have rational roots, they have to appear in that list. It does absolutely nothing for us in finding irrational roots. So finding rational roots, awesome. Finding irrational roots, lame. It does nothing for irrational roots. So what if our polynomial has no rational roots and all we have are irrational roots? How in the world do I solve it? Graph it. Remember, real roots, whether they are rational or irrational, roots that are real numbers are simply the x-intercepts of the graphs. If the roots are complex numbers, they're not going to be x-intercepts of the graphs because we can't graph complex numbers in the xy coordinate plane. But the real number roots will be x-intercepts of the graphs. So if I can graph it, I can find the x-intercepts, or at least approximate them, estimate them. So how do I graph it? On my calculator. For example, estimate the roots of x cubed minus 2x squared minus 4x plus 2 equals 0. I'll give you a minute or a few seconds to grab your graphing calculator and get it out, and you can do it with me. Oh wow, that was fast. It's almost as if you have the ability to pause time or something. Okay, here we go. Here's my graphing calculator. You've got yours. You can do it as I do it. So we're going to graph this on our calculator. So we're going to go to y equals. We're going to enter in our entire equation minus the equal 0 part, just the left-hand side. So x, which is the button right below mode, cubed, and I can just use the caret key, that little arrow thing above the division sign, and I can put in a 3. Use the arrow button to move out of the exponent. Do minus 2x, and there's a x squared button on the left-hand side of my calculator, minus 4x plus 2. X cubed minus 2x squared minus 4x plus 2. I put it in my calculator under y1. Okay? I'm going to go to zoom, which is the middle button here. I'm going to choose number 6, zoom standard. So I can scroll down to number 6, or I can just type the number 6, hit enter. That sets my window to be negative 10 to 10 on the x-axis and negative 10 to 10 on the y-axis. And that is enough, generally, to see all of my roots. I know this is a cubic equation. I know it should have 3 roots. I see 3 places where it crosses the x-intercept. Where it crosses the x-axis, I mean 3 x-intercepts. That means all 3 of my roots happen to be real numbers, so I can find them. My calculator can do that for me. To do that, I click second, calculate, which is the trace button. And then I go down to number 2. I want to find a 0. Remember, x-intercepts of my graph are the zeros of my functions. So I want to find a 0. So I click enter. Now there are 3 different ones. So my calculator wants to know which one I want to find. So it asks me 3 questions. First, it asks me the left bound. So I have to use the arrow buttons on my calculator, and I have to move to the left of the 0 I want to find. So let's say I want to find the furthest left one. So I move someplace to the left of it. See how my cursor is now on the graph to the left of the x-intercept I want? Good. Then I click enter. And it asks me for a right bound, so I need to move to the right of it. This is telling my calculator where to look. So it's going to look between the left and the right bounds. And then it asks for a guess. So I can just leave it where it is and click enter again. And now it tells me what my 0 is. Now is it exactly negative 1.514137? No, the decimal keeps going forever. It's an irrational number, so the decimal doesn't end. But my calculator has truncated it. It's cut it off there at 6 decimal places. So my answer is, or one of my roots, the roots are approximately Let's use a squiggle equal sign. And that was negative 1.514. Okay, let me find another one. There are 3 of them, so I'll do the same process. Second, calculate number 2, which is 0. I move to the left of what I want to find. Any place there is good. I move to the right. Click enter. Guess. Right where I am is a good guess. And it tells me 0.428. So let me write that one down. 0.428, comma. Let me go back and find the third one. Second, calculate. Number 2, left bound. That looks good. Enter. Right bound. That looks good. Enter. Guess. Enter. And it tells me 3.086. 3.086. Now again, are these exact? Absolutely not. But they're approximations. So that's better than nothing. And since the rational root theorem doesn't apply to this equation, I don't have a way to solve it on its own, except to just guess some random irrational number and see if it works. Not a very good approach. So graphing it gives me a good guess. And in the real world, that's all I really need. Another example, x to the 4th minus x cubed plus x squared minus 3x plus 1 equals 0. We will graph it. I will go to y equals. I'll clear out the graph I have there by clicking the clear button. Or the equation. I'll clear that out by clicking the clear button. I'll do x to the 4th, so x, caret key 4, use the arrows to get out of my exponent, minus x, caret key 3, use the arrow key to get out of my exponent, plus x squared minus 3x plus 1, zoom 6. It graphs it. Hey, this one only crosses the x-axis twice. If I want to see a better view of it, I can go to zoom, and number 2 is zoom in. I'll click enter. If you notice, there's a little dot at the very center that's flashing. So that's, I'm telling it where I want it to zoom in at. So I can just click under there, and it will zoom in for me. Give me a better view of these things. There they are. So I can now clearly see it only crosses twice. But it was a 4th degree equation. That means 2 of the solutions, 2 of the roots, are complex. So they don't show up on my graph. Okay, so I can find these 2. I go to second, calculate, number 2, left bound, right bound, guess, 0.368. So approximately 0.368, comma, back to my calculator. Second, calculate, 0, left bound, right bound. There we go. And guess, enter, 1.43, 1.428. And I'm done. Cool. Alright, now on to linear interpolation. Let's take this real-life scenario. I've got a table here with actual real-world data. The U.S. population estimated in millions for each of the years over the last 110 years. So notice the years go up by 10 every time. That's because the U.S. government takes a census of the population every 10 years. The last time they did it was in the year 2010. So that's the most recent data point I have. The census means they try to get data from every single citizen of the United States. And part of that is just counting how many citizens there are, and that's the U.S. population. Okay, so if this only gives me data for every 10 years, what if I wanted to have an idea of the population in between those years? So, for example, find the approximate population of the United States in 1953. Well, I've got 1950, and I've got 1960, I don't have 1953. So what I'm going to do is a process called linear interpolation. I'm going to interpolate, I'm going to look between two values in my data. That's what it means to interpolate, is to look between two values. And I'm going to get an approximation of what it would be. So I'm going to set up a proportion. This gap from 1950 to 1960 is 10 years. The population in that time goes up by 28 million. Somewhere in there is 1953. And the gap between 1950 and 1953 is 3 years. So there is some gap between 151 and the population in 1953. So we'll call that X. Okay, so all I'm going to do then is set up a proportion. I'm going to take 3 over 10 equals X over 28. So the small gap over the big gap equals the small gap over the big gap. Cross multiply. 3 times 28 is 84. So 10x equals 84. X equals 8.4. So what is the approximate population of the United States in 1953? Well, it's 8.4 more than what it was in 1950. So I need to take 151 plus 8.4, and I get 159.4. So approximately 159 million. Why do I have to say approximately? Because this is not exact at all. I really do not know what the population was in 1953. I'm just making an estimate. How good is the estimate? I really don't know, because I don't know what the population was in 1953. So I've made an estimate based on the pattern, or the increase, from 1950 to 1960 being uniform over each year. Was it? Not exactly, but it was probably close. All right, find approximately in which year the population was 140 million. So this is backwards. Now I've got the population. I want to know what year. So I look, and 140 million is between 132 and 151. So somewhere in there is 140. Okay, so it must be somewhere between 1940 and 1950. All right, so let's call that increase from 1940 to my mystery year, my X. It's an overall increase of 10 years, from 1940 to 1950. My increase from 132 to 140 is 8. My increase from 132 to 151 is 19 million in this case. So I'm going to set up my proportion the same way. Small gap over big gap, X over 10 equals small gap, 8 over big gap, 19. Cross multiply 19x equals 80. X equals 80 divided by 19, which is about, approximately, because this is an irrational, this is a rational number, but it is a long decimal, 4.21, approximately. Alright, so in what year was the population about 140? Well, I take 1940 and I add to that about 4 years, because I'm not going to take fractions of a year. My estimation is not exact enough to be able to make that worthwhile. So I'm going to say in about 1944. 1940 plus 4. That's it. What are we really doing here? Well, we're assuming that the population growth is linear. We're assuming that its graph is a line. Is it? Well, here's a graph. Is it a line? Not quite. It's not straight. Look at that. It's not a constant slope, but it's pretty darn good. This is a graph from 1900 all the way to 2010. So it's pretty darn close to linear as far as real-world data is concerned. So it is increasing at a fairly steady rate, but it's not completely steady. It's not the constant slope. So are my answers going to be exact? No way, Jose. It's not a constant slope. It's not perfectly linear. So why do I do it if it's not going to be exact? Because usually it's all we can do. If I didn't take a census in 1953, I cannot know the population in 1953. So I can make a good guess based on what it was in 1940 and 1950. 1950 and 1960. How can I make a better guess? How can my approximation be better? Well, in a couple of ways. One, I can take better data. That means I could take a more frequent census. I could take a census every 5 years. And then if I wanted to know 1953, I could take 1950 and 1955. And I'd have a better approximation. I could take a census every 2 years. I could take a census every year. Why don't I? That's incredibly expensive and time-consuming and difficult. And it's not worth it. At least to the U.S. government, it's not worth it, and that's logical, because it's very, very expensive and time-consuming, and it takes almost a whole year to take the census. I could take a better linear approximation. What does that mean? Well, instead of picking the two closest data points, so for 1953 I picked 1950 and 1960, I can use a different method to describe that linear relationship. Maybe I could take 1900 and 2010 and assume that the linear relationship is fairly consistent over those 110 years. Or maybe I just want to go from 1940 to 1970. Or, what if there's a different way that I can model that linear relationship? Hang on to that thought until we get towards the end of the semester, and we will do some linear regression to come up with that. Or take AP Statistics. Here are your immediate practice problems. Number 1, graph and estimate the real roots to 2 decimal places. So on your calculator. Be careful. In order to do a negative, you're not using the minus sign. You're using the button next to the decimal point. That is a negative. Do not press minus x to the 4th, because then it's trying to subtract and it doesn't have anything to subtract from. So use the negative button, which is the button to the right of the decimal point. And number 2, what was the approximate population of the U.S. in the year 1973, using the data in the table above? That is the end of sections 8.8 and 8.9.